So we begin our process of looking at chapter 5, and we're going to be learning probability. In this chapter, in section 5.1, we're going to construct sample spaces and know the probability rules, understand the law of large numbers, and interpret probabilities, the observed probability versus the expected probability. Objective 1, construct sample spaces and understand the law of large numbers. So we start out understanding what probability is. It's the chance of an event occurring. A probability experiment is one in which we do not know that any individual outcome will be, but over a long series of repetition of the experiment, the probability of an outcome is determined. For example, if we toss a fair coin, we do not know what the outcome of a single toss will be, but we do know that the outcome of a long series of tosses will be about half heads and half tails. The probability of an event is the proportion of times that the event occurs in the long run. So for a fair coin, that is, one that is equally likely to come up heads as is tails, the probability of heads is 1/2, and the probability of tails is 1/2. So if we conduct the experiment of the tossing of the coin over a long period of time, the law of large numbers says that the probability of that experiment is repeating again and again is the proportion of times that the given event occurs will approach its probability, what we call the expected probability. A sample space is the collection of all possible outcomes of a probability experiment. So, for example, the toss of a coin, the sample space is heads or tails. The roll of a die, the sample space is 1, 2, 3, 4, 5, and 6. Selecting a student at random from a list of 1,000 at a large university, the sample space consists of 10,000 students. A probability model is one in which we are able to determine over the long period of time what probabilities will be. So sometimes we are often concerned with the occurrences that consist of several outcomes. For example, when rolling a die, we may be interested in the probability of rolling an odd number. Rolling an odd number corresponds to the collection of outcomes of 1, 3, or 5. The sample space, which is 1 through 6, the odd numbers comes from this sample space. In general, a collection of outcomes of a sample space is called an event. Once we have a sample space, we need to specify the probability of each event. This is done with a probability model, and sometimes we call it expected probabilities. We use P to denote probabilities. For example, we denote the probability that a toss of a coin lands heads by P of H, or P heads. In general, A denotes an event. The probability of event A is denoted by P of A. So we're going to learn probability rules, compute and interpret probabilities. We're going to look at observed versus expected. There are two major rules in probability. The first rule is, for each event or outcome in an experiment or survey, the probability is between 0 and 1, usually a decimal. And we represent it, the rule, the following way. 0 less than or equal to P of E, the event, is less than or equal to 1. Also in a probability experiment, the sum of the probabilities of the sample space equals 1. That is, the summation of all the probabilities is equal to 1. Note, if A occurs, then P of A, if A cannot occur, then P of A is equal to 0. If P of A is certain to occur, then P of A is equal to 1. Probabilities with equally likely outcomes. In this case, we can actually determine a probability model and get the expected probabilities. If a sample space has n equally likely outcomes and event A has k outcomes, then P of A is just the number of outcomes in A divided by the number of outcomes in the sample space, which is k over n. For example, in Georgia's Cash 4 lottery, a winning number between 0000 and 9999 is chosen at random with all possible numbers being equally likely. What is the probability that all 4 digits are the same? Well, the solution is the following. The outcomes in the sample space are the numbers from 000 to 9999. So there are 10,000 equally likely outcomes in the sample space. There are 10 outcomes for which all the digits are the same. Therefore, the probability is, the probability of all 4 digits the same is equal to 10 divided by 10,000. And if we put it in decimal form, it's 0.001. So if the model has equally likely events to occur, we can create the expected probabilities under a model. A family, for example, has 3 children. Denote a boy by capital B and a girl by capital G. We can denote the genders of these children from oldest to youngest. For example, GBG means oldest child is a girl, the middle child is a boy, and the youngest child is a girl. There are 8 possible outcomes: BBB, BBG, BGB, BGG, GBB, GBG, GGB, and GGG. Wow. Some of these outcomes are equally likely. What is the probability there are exactly 2 girls? We're going to answer that question. And then what is the probability that all 3 children are girls? Well, our solution for the first case is, of the 8 equally likely outcomes, there are 3 outcomes, BGG, GBG, and GGB corresponds to having 2 girls. Therefore, the probability of 2 girls is nothing more than the 3 events divided by the sample space, which is 3 divided by 8. Of the 8 equally likely outcomes, in part B, the 2 outcomes BBB and GGG correspond to having all children the same gender. Therefore, the probability of all 3 are girls is really 1 over 4, right? Cases, right? Well, actually, that should be 1 over 8 in this particular case. This is wrong. It's 1 over 8 of having all girls. Okay? In general, if things are equally likely to occur, we can count for each space that we have if there's 2 possible outcomes in the first event and there's 2 possible outcomes in the second event, and there's 2 possible outcomes in the third event, we can just multiply these and get the sample space of 8. In this case, for the first child, there were 2 possibilities, a boy and a girl. For the second possibility of the second child, there were 2 possibilities, a boy and a girl. In the third child, there were two possibilities, a boy and a girl. So 2 times 2 times 2, there were 8 possible outcomes in the sample space. So sampling from a population can also be considered a probability experiment. And the population is the sample space. The members of the population are equally likely outcomes. So if we know the total population, for example, we can calculate the probabilities based on that sample. Note, these are the outcomes that may change over time. There are 10,000 families in a certain town categorized as follows: owning a house, owning a condo, renting a house, and rent apartment. Here is the sample from this population. What is the probability that a sample family owns a house? Well, if we randomly select from this, we find that of these, 4,753 own a house. And the population that we have, or families, is 10,000 families. So out of this, 4,753 families own a house. The probability is 0.4753. The number of families who rent, well, there's two possibilities that can occur. We have renting a house or renting an apartment. We have to add those two together, and we end up with 3,769. Therefore, the probability of renting in this small town is 0.3769. So sometimes we want to know whether an event is unusual. So an event that is unusual is one that is not likely to happen. In other words, an event whose probability is small, there are no hard and fast rules as to just how small a probability needs to be before an event is considered unusual. But we will use the following rule of thumb. Any event whose probability is less than 0.05 is considered to be unusual. Example: in a college of 5,000 students, 150 are math majors. A student is selected at random and it turns out to be a math major. Is this unusual? The solution is the event of choosing a math major consists of 150 students out of a total of 5,000. The probability of choosing a math major is just 150 over 5,000, which is 0.03. This would be considered an unusual event. Objective 4. Approximating probabilities using the empirical method, which is what we call the observed probabilities. When events or outcomes are unclear to create a probability model for equally likely events occurring, experiments or surveys are conducted over time to find the probabilities. In many cases, the probabilities are the relative frequencies of the event under the data collection process. The following formula is used to calculate the observed probabilities. The probability of an event is the frequency of the event occurring divided by the total number of trials. Note, due to the nature of the large numbers, as the experiment or survey is conducted many times, the observed probabilities approach the expected probabilities. So, the law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that a particular outcome occurs is likely to be close to the true probability of the outcome. So the empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. For example, in 2010, there were 2,046,935 boys and 1,952,451 girls born in the U.S. Approximate the probability that a newborn baby is a boy. We compute by the number of times the experiment had been repeated, the number of births, right? The total number of births was, here it is, 3,999,386. The proportion of births that are boys is just 2,046,935 divided by those total births. We get the answer of 0.5118, right, for a boy. But this is the observed value. Observed value. The actual expected value would be 0.5. So in this chapter, we discussed the law of large numbers and the definition of probability, sample space, and event. We also looked at how to compute probabilities with equally likely outcomes, the expected probabilities, the rule of thumb for determining when an event A is unusual, if P of A is less than 0.05, and how to approximate probabilities using the empirical method, or what we call the observed probabilities. That ends chapter 5.1. We will now go to 5.2.